Hey guys, my name is Adrienne and welcome to Organic Chemistry 1, Part 7 of these recorded sessions. Today we're going to be going over, for most of y'all, Chapter 7, or in general, alkyl halides and nucleophilic substitution reactions. So let's look at our agenda for today. We have here alkyl halides, nucleophiles and bases, nucleophilic substitution reactions. So very straightforward, but these are, especially the last two topics we're going to be going over, these are perfect things, perfect topics to go over because they'll be carried over for the rest of the class and even in OChem too. So let's get started with alkyl halides. And again, I'll have the titles or the topics up here for each page we do, so you guys can navigate this video better. So okay, alkyl halides. First things first. There's classification. So same thing with kind of hydrogens and carbons, there's primary, secondary, things like that. But with alkyl halides, there's also a methyl halide, right? And then you have primary, secondary, tertiary. Again, no quaternary, just like the hydrogens. So with methyl, it's literally just going to be a methyl. We know methyl groups are just one carbon, right? So a halogen with one carbon. So now you just keep adding R groups. Right there, right? And then nothing too crazy. It's just the same concept we've already learned, but just review, right? So that's it. And this will come in handy later because our nucleophilic substitution reactions actually require, some of them require tertiary, some of them require methyl halides, so things like that. And now with classifications, there's more, I guess, terms or types that we're going to see. We've seen some in the past lessons, past chapters. There's certain like double bonds, things like that, or groups. Same thing with alkyl halides. So there's going to be vinyl, aryl, allylic, and benzylic. And we don't use this too much because when we name them, we name every single thing. So we don't really see these a lot, but they're good to know. And if anything, these are just like one of those things that's like, if you don't know them, you don't know them. But most likely you'll see them in their nomenclature form, not this way. But nothing too crazy. So those are the types, the new types of alkyl halides. Okay. Now also with this we have nomenclature. Nomenclature rules are going to be the same. So IUPAC stands, right? So let me see. I'll have it over here. Nomenclature rules are the same, but now instead of working with propyl groups, isopropyls, butyls, we're going to be looking at halogens, right? So halides, bromides, fluorides, things like that. Still the same. We're still numbering them. They're still substituents. We number them from lower to greater, things like that. So nothing too crazy. And then common names. Common names are just going to be this way. Carbon, chain, plus halide. Halide. There. Common names is going to be carbon chain and then plus your halide. So let's say you have a pentane group. Pentane, and then it has a bromine at the end. Pentane bromide. Nothing too crazy. So let's do practice. Alkyl halide. Again, practice. So let's see. Find the common names. Also, common names are like the arrow, things like that. So find the common names of these. And last one. Okay. And then let's see, do we have room for these? Yeah, we do. So for the two, find the IUPAC. So IUPAC is the one with all the rules, right? Um, so did it do it? 1, 2, 3. Let's see. Two. Actually, let's do just two because you know we ran out of room. But okay, and there's gonna be um a CL. Actually, let me redraw that because that's kind of let me redraw that. I wish I had like a bigger eraser, but or maybe I just shouldn't make mistakes, right? Okay, so I'm gonna draw it this way. Okay, and then so I can have CL there. Okay, so pause the video, take a minute. Give me all the names. Okay, so for the first one, what do you guys get? Common names again, right? So we know this is an allyl group, so allyl bromide. Not too crazy. This one is gonna be a what? Right, this one's gonna be just, aryl chloride. And then this one, we have what kind of chain is this? Right. So this is a common name again, isopropyl bromide. And then over here, tert butyl bromide. So that was it. Those are all the common names, right? Now let's do the IPAC with all the rules. Rules. We've known what the rules are for some time now, so this shouldn't be a surprise. But we know that we find the longest chain. We start with the lower substituents. So for numbering this way, 4, 5, 6, blah 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 blah, 8. So this is the substituent, substituent, substituent. Right. So you should have gotten 2 fluoro, 4 isopropyl, 2 6 dimethyl octane. Right. Not too crazy. And let's do this last one. You should have gotten again. We know the rules for IPAC. We know that we follow the longest chain, and you know, if to find where to start, we go alphabetically. If we can do if these two substituents are equal. So alphabetically, chloride is um, the first one, and the methyl is the second one. So 1, 2, 3, 4. 1, 2, 3, 4. So either way, clockwise or counterclockwise, we'll get to 4. So it doesn't matter. So, but the big thing with this is that don't forget trans. This is a trans, right? 1 fluoro, 4 methyl, cyclohexane. So don't forget the trans. It's probably that's why I did this one. So don't forget trans. Don't forget R and S, and all that stuff. So okay, so that's all with the alkyl halides. Going over it, kind of previewing it, reviewing it. So let's get started with the more fun stuff. Okay, so what's our next? nucleophiles and bases. So this is going to be a lot of concept, and we'll do some practices as well, but a lot of trends, a lot of what constitutes as nucleophile, what constitutes as base, things like that. But first, let's go over polarity. So with polarity, we already know if there's any kind of dipole moment, things like that, where things going. So here, halogens are extremely electronegative, so obviously they're gonna make polarity if they're present. So that's why this is important. Polarity in this particular topic is halogens are highly electronegative, right? So most likely, pulling electrons away. So making it polar, making the molecule polar, making a certain part of it polar, things like that. And now, extremely polar. So if they're pulling it, they're gonna be electron rich, right? And then the rest of the molecule will be electron deficient. So okay, now we have reaction types, and this is kind of a preview of the nucleophilic substitution reactions. Reaction types. If we have nucleophiles, it's gonna be a substitution. Substitution. If it's a base, it's going to be elimination. And this one is actually going to be the next chapter or the next video. So, elimination. So just write it out. Okay, so not too crazy. And this is probably the most important. I'm going to actually color this ink because you can tell once we go through the rest of this topic, you'll be able to tell immediately if it's going to be a nucleophile or a base, right? So from there, you're 50-50. So it must be substitution or elimination, right? So, but if it's a nucleophile, it's for sure going to be a substitution. If it's a base, it's going to be elimination. So that's kind of where you have to think with those. Kind of make it easier for yourself, right? Okay. So now next on that is the leaving group. The leaving group is important because we can just substitute or eliminate every single thing on our molecule, right? So we have to choose which one of these is the best candidate to switch out or to eliminate, right? So that's kind of why we talk about the leaving group. But other than that, other than knowing that concept, pretty much you'll be working a lot with halogens, and those are going to be pretty much the leaving group, those by default, right? Because they're the best leaving group. So here, since you guys are, this is just a review. So the better the leaving group equals weaker the base. Weaker the base, right? And this is kind of the trend for that. So this is the periodic table. And let me actually color this. So the leaving group will do blue. And the leaving group, it increases down this way, right? So leaving group increases this way. And the base, let's do green. And the base, and since it's opposite, the base increases this way, right? So increasing basicity. Increasing basicity is the green. And then for the blue, increasing leaving groups, right? So that's all you need to know for that one. And also, and from that you can draw a lot of conclusions. Like, let's see, if it's a Good leaving group? Oh, not GG. It's supposed to be LG. Okay. Good leaving group gonna be consist of, if it's good, it's gonna be a weak base, obviously, and also strong conjugate acid, and then vice versa. Right. So all those kind of like there's also well you guys know by now there's a lot of different names for a lot of different things, right? So you can get asked these different things. So which one of these is gonna have the weakest conjugate acid? So you look for the weakest leaving group, right? So things like that. It's kind of um, interchangeable. If you're getting asked which one of these is strongest leaving group, look for the strongest conjugate acid, or the weakest base, things like that. So all interchangeable, and that's a lot. That's like the thing with a lot of topics, a lot of even not even in NOCM in general. So actually like life lessons, there's a lot of like interchangeable things that just because it's not asking for this one thing does it doesn't mean that it can't be this other thing. So life lesson. Okay, so that's that with leaving group. Pretty much this trend is all you need, and then from there you can kind of just go off of it. So let's go to our next subtopic, I guess. So we're still with nucleophiles and bases, and now we have actually the actual um, nucleophiles and bases. They're pretty much the same. Um, so how can you tell them apart? Structurally the same, similar. They have lone pairs, they have pi bonds. So lone pairs, pi bonds, things like that. The way they differ in is what they attack. So differ in attack. So for bases, they go after protons. Protons. For nucleophiles, they go after electron deficient atoms, right? Electron deficient. So, and you can kind of, this is an example of what you'll kind of look for. So let's say we have this molecule, we have a halogen here, we have a proton there, and let's see, we have a nucleophile out here, we have a base out here. Where are they going to attack? Right, so bases attack protons, so it's going to attack this proton, right? And then nucleophiles attack electron deficient things. So since this halogen is here, that means the polarity is up here, right? So this one making this electron rich, making this atom electron deficient, so it's gonna attack right there, right? So that's what you're looking for. And other than that, um, that's all. So, and I guess as well as basicity, just the definition, and this is where a lot of this is actually it's they're so similar, but you know, this is kind of what the official definition of them are. Basicity is, donate um, its electron pair to the proton. So let's see, what is it? Readily donates um, its electron pair to proton, which we already know. So proton keyword for base, right? And then this one donates its its electron pair to um, other atoms, electron deficient atoms, electron deficient atoms, right? And another thing with basicity is that basicity is more thermodynamic, while nucleophilicity is more kinetic. So just a little concept there for you. You know, nothing too crazy. So that's all you need to know. Basically the focus should be this, the way they attack, right? That's the main thing you guys should get ground out of this. So, and if anything, you can just draw this and you know what it means, right? Base goes for the hydrogen, nucleophiles goes for the electron deficient. Boom. That's all you need to know. Okay, so let's move on to, let's see, what else do we got here? Nucleophile and bases. That's pretty much it with those. I guess just to summarize, you know, stronger the base, stronger the nucleophile, because they're so similar, right? Two, nucleophilic, right? So conjugate is better than non, right? So, and also this negative here is going to be a better nucleophile than non-negative, because we know nucleophiles like um, electron deficient things, right? So, and this is electron rich. So, yeah. Okay. Three. And basicity and nucleophilicity also have the same trend. So both of them, again, this is the periodic table, increase this way, right? Increasing basicity, nucleophilicity, right? So that's easy. So you see how they're super similar, but the thing that differs them is where they attack, right? And then let's see, four, not similar, and we'll talk about this more once we get to the substitution. Not similar in steric effects. Effects. So primary, secondary, tertiary, those type of things. So steric effects, not similar to steric effects. Steric effects affect, and here, affect nucleophilicity, not basicity. Not basicity. So that's the only thing with that. Right. And let's see, I think I should have enough room. Yeah, I should have enough room. So no, I'll do another page. Okay, so that's that. That's like a summary of it. And now we get into kind of the last of it, nucleophiles and bases, and how to kind of support which one you're choosing, right? Because they need, like, think of it as like a sidekick. So this kind of will, these solvents will really cement um, if you choose nucleophile or base, right? We have protic and aprotic. So protic is gonna be, you know, it has H bonds. So these are solvents, you know, other molecules that are just in the solution or in the reaction. So this has H bonds, no H bonds. So this can solvate cation, anions. This solvates only cations. So that's kind of that. Nothing too crazy, and also kind of just a little bit more info on these, and you kind of see these later. Also, kind of taking into account the steric. So this protic is shielded. Oh, shielded, and then this is naked. Okay, so nothing too crazy. And another thing with these is that they affect um, nucleophilicity. So, and let me do it here. For protic, if it's in a protic solvent, this is the periodic table again. Nucleophilicity increases this way, increasing nucleophilicity. But if you're aprotic, nothing changes, right? So you guys don't use this a lot, but just good to know, like some increasing nucleophilicity. So the questions you'll get from these protic, why this is important, things like that, is like, let's say this thing is in a protic solution. What happens to nucleophilicity, right? So what's the things like that. So this thing is in an aprotic solution. Um, what happens to nucleophilicity if we're given these molecules, these reactants, right? So that's kind of what you would look for those. But again, nothing too crazy. It's not really high yield. It's just like it's there just in case, right? So let's do some problems and see what damage we can do. So nucleophiles and bases. Okay. So here, one. Which is the most and least polar? So label the most and least, right? CHCl3. Oh, lots of like typos today, huh? This is gonna be Cl2, so you guys kind of already know where this is coming from. This is going to CH or 3Cl, right? So okay, and then let's do this one. Which is the best and worst leaving group? So again, there's going to be two answers for the most and least, right? Or for the best and the worst, I should say. NH3 and minus. And then let's see. 2, 3. Which one is the most and least nucleophilic, right? And this one's a good one. Label if protic or aprotic. CH3CN, H3COOH, H2O. Okay, lots of writing, but take a minute, pause the video, and tell me what you got. So this is what I got. Let me do this one. Okay, the most you guys should have gone for the most is this one, most polar, and then this one for the least, right? And why? Because this one is evenly the dipole moments are evenly spread out, right? Because there's 4 CLs. Cl, 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 and they're all, um, again, they're all canceling each other out. This one does not. It's only one Cl, so everything is going that way. Okay. So most, least, and then you can even order these. So most, second, third, fourth. Right. So now I'm gonna change the color for each one just because. So the best and worst leaving group. Least, you should have gotten this one, and then for best, you should have gotten this one. So best, why is that? Um, Again, going for the trend, you just follow it. Oxygen versus, nitrogen. And again, it's already, this one's already negative, right? So that's going to be the worst one because it's not going to stand by itself. It's not going to, the conjugate is not great, right? So, um, oh, I didn't do one for these, the nucleophile. Let me guess. I was like, no wonder I had room because I was thinking I didn't have room. So three, we have, what do we have here? Nucleophiles, CH3OH, CH3O minus, H3S minus, CH3SH. Okay, sorry about that. That was crazy. Okay, take a minute for that one. You should have gotten. This one's the least, and this one's the most. Most nucleophilic, right? And why is that? So oxygen and sulfur are very close in the periodic table, but um, oxygen is less nucleophilic because it's more electronegative than sulfur. So just yeah, just remember that oxygen is always going to be more electronegative than sulfur, and we know nucleophilicity is to donate its atoms, its electron pairs, right? So oxygen is not going to want to donate because it's more electronegative. It's going to want to keep those electrons to it. So that's all there is to that. And now let's do this one. For this one, you guys should have gone protic. This one, aprotic. This one's protic, protic. And the easiest way to do this is, again, hydrogen bonds. Protic have hydrogen bonds, aprotic don't. So that's all there is to that, right? Not too crazy. And yeah, let's go on to our last topic. I feel like we've gone through a lot, but this last one should be fairly not too crazy because let's see, nucleophilic substitution reactions. So for this one, um, you you're gonna do elimination as well the next lesson. I like to compare them side by side, so I make a column, a table, or type thing. So um, and I guess just a little note over here: SN1, SN2 um, occur on sp3 carbons, not, and we just talked about this earlier with the types, not on vinyl and aryl halides, right? So not on this one or not on this one. And you'll see later why once we start doing the list, or you guys probably already know. So okay, so let's divide this. We're gonna have let's see, SN2 went first, so SN2 here, and then SN1. Okay, so SN2 is second order, and it's one step because of that, right? It's fast. Second order, one step, and the rate is gonna be K, RX, and then nucleophile, right? So both of those count. Um, it's gonna have one intermediate, nothing too fancy. It's just one intermediate, and it's gonna the way it attacks, it's gonna backside attack is preferred attack. So it's gonna flip the molecule. So flip them from R to S or S to R, right? Opposite of leaving group, right? Opposite of leaving group, so it's gonna do that. And this is where the classifications come in. It prefers methyl over primary, over secondary, over tertiary, right? So, and I think it has, since it's one step, it wants to get out of there with as little hassle as possible. So we want the clearest path. So methyl groups are very unhindered. They don't have a lot of stuff around them, so that's going to be the fastest. So, and this occurs best in aprotic solutions or solvents, aprotic solvents. And these are just examples you'll see. DMSO and VMF and UMPA. Okay, trying to get into the space of that one, but yeah. And also for this one, we said the substitution prefers nucleophiles. So both of these will like nucleophiles, and it's in the name, right? But this one, strong nucleophiles, strong nucleophiles, right? Okay, so let's do SN1. So this is going to be first order, and it's two steps. The rate, we don't care about the nucleophiles because it's two steps. We just care about the alkyl halide, right? RX, whatever that is. And then this one has two intermediates, and one of them is a carbocation, which is the first one. Forms carbocation. Forms carbocation, and this one can do either front or back side. So front, back side, so it doesn't matter. And this is gonna, since it prefers either one, it's always gonna make racemic mixtures. So 50-50. Racemic. 50-50. Right, so racemic is an important one. And then with this one, it's going to be opposite. This prefers tertiary over secondary, primary, methyl classifications, right? So there's that. And since it makes carbocations prefer also same thing. Tertiary over secondary, primary, methyl, right? So those are that and weak, and that's how you can kind of tell. And again, how can you tell about between strong and weak nucleophiles? The charge, right? The more negatively charged, the more stronger it is. So there's that. That's all you need to know. This is like a summary of it, and a good summary. Um, nothing too crazy. All of these are good to, they're important, obviously, but just to point out some stuff. This one, um, a lot of students forget about this. Rate, right? Backside, right? So it's gonna flip it, so R to S or S to R. Um, oh, I just realized this one, aprotic over here, aprotic, and obviously this one's gonna be protic. So protic, right? And any protic solvents that are that have what's it called hydrogen bonds. So nothing too crazy. So I feel like all of these are important, but these are the things to keep in mind, especially once everything is mixed up, you're gonna need to figure out, okay, what clues can I choose, or what clues do I have to make sure that this is what um, to make sure the reaction is undergoing substitution SN2 or SN1, right? So right over here again. This one racemic mixture, that's the important one. Racemic um, methyl. Okay, right. So nothing too crazy. So let's do some examples and see what we got. See what we see. Okay. Nucleophilic substitution reactions. Okay, so let's do. Mm, let's do this one. What happens if this is doubled, and this is a reaction, Br plus OH, okay, let's see, and let's do this one, which is most likely to follow second order. We have H3Br, CH3, 3CCH2, Br, CH3, Br. Okay, then let's do, I can put another one here. 3, which alkyl halide will react fastest in CH3OH. So these are all good questions because they kind of mix all the things we just talked about. So, you know, and you're not gonna get a straightforward, what's this, what's that. It's kind of connecting everything. So, okay. So take a second, take a minute, pause the video, and tell me what you guys get. Okay. So, first one, what do you guys get? I got um, rate stays the same. And why? Because what kind of reaction is this? This is a SN1, right? And we know SN1 is rate equals Rx, right? We don't look at the nucleophile, right, which is this. And actually from that we can say that this is actually a weak nucleophile because it's not negatively charged. Weak nucleophile, and we can We can tell that this is an SN1 as well because this is a what? What kind of alkyl halide is this? A tertiary, right? And we know tertiary alkyl halides are preferred in SN1. So we have a tertiary alkyl halide with a weak nucleophile. That's an SN1. And therefore, the rate, we only care about the alkyl halide. So even if we double the nucleophile, it's not going to do anything. The rate stays the same, right? So which one of these follow the second order? So that's easy. We know second order is SN2. Let me change the color. SN2. So we're looking at SN2, and SN2 prefers what? Methyl to over, primary, secondary, tertiary, and we know this one is a methyl halide. This one is going to be a primary, and this one's a secondary. Actually, this one's a primary as well, right? So this one, and you can just draw this out as well. This one is like this, H, 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 that's a methyl. This one is something like this, Br, so that's a primary. And this one's just this, Br, that's a primary, right? So methyl is what we want. And now fastest than CH3OH, so the solvent. So we know this is what kind of solvent? Right, a protic, right? So protic solvents are preferred by SN1, right? So SN1, so which one of these will work in SN1? We know SN1 likes tertiary way more, so we can label these. This is a secondary, primary, primary, tertiary. So our choice is that one, right? So not too crazy, as long as you follow the rules or the steps and the clues, right? Don't forget to look at the nucleophile, what type it is. The best thing to look at is the classification. If it's tertiary, automatic SN1. If it's primary, automatic SN2. That's all. And then if you're stuck there, especially if it's SN2, if it's secondary, then you look at the nucleophile. So is it weak or strong? Or the solvent? Is it protic or aprotic? Right? So not too crazy. You're not gonna get stuck with like, oh, these are all the same. What do I choose? You're always gonna have something to break that tie. Okay? So I have a couple more questions for you guys, but those are good questions as well. So um, you guys should be set after that. But let me give you a couple ones because I looked for them, so you guys can see them. So what number was that? 4. Which solvent affords the faster reaction? Reaction. So, and we have this. Ooh, that's really ugly, but okay. Yeah. CH3OH, and then we're choosing between either CH3OH or DMSO. So this is going to be A, and then B, and then our product. We don't really care about the product, but I'll write it anyway. Plus HCl, and then let's do this one. This last one, determine the product. Okay, so take a second, pause the video, and get back to me. Okay, so before even looking at these, right, this is what we're getting asked. What kind of reaction is this? Right, SN1, right? SN1. And why? Because this is a tertiary, and we know tertiary is always with SN1, and this is a weak nucleophile. Nucleophile. And so if it's SN1, we're looking for a solvent that's protic, right? So protic. So which one of these is protic? A, right? With the H bond. So, boom. Super simple. Um, that's it. And we know DMSO is aprotic, so that wasn't going to be it, right? Aprotic. So that would have been with SN2. Okay, now let's go to this one. Determine the product. First again, what type of reaction, SN1 or SN2? SN1 again, right? Because this is tertiary, right? And this is, well, we just set it up here, weak nucleophile. Weak nucleophile. Okay, so with that being said, our product should be what? This is what you should have gotten. You should have gotten two products, first of all, right? Because SN1 can do front side or back side, so two options. So you should have gotten something like this, CH3, or O, right? So it could have gone attacked with the BR or with the methyl group, right? So, and again, that's called racemic, right? Racemic. So that's all there is to it. Nothing too crazy. That's pretty much all you need to know. And obviously, if it was, which one of these did the backside and front side? Let me do it in a different color so we can see better. This one's the front side attack, and this is the back side. So it literally just went to the other side, right? Not too crazy. Um, so other than that, that's pretty much it. Um, yeah. And again, this is the topics we covered, right? The most important here is probably the substitution reactions because it has a lot of moving parts, but I feel like the questions, if you kind of step by step, you'll get them. There's enough clues there, right? And with that being said, that's all I have for you guys today. And if you guys have any more questions, or have any other problems, feel free to watch the other videos and catch me there. So again, thank you guys, and I hope to see you guys later. Bye.